Dear students, in this session we are going to learn about phase equilibria in sulfur system and a reduced phase rule, that is two component system. The contents of this session includes phase equilibria in one component system, that is sulfur system, and reduced phase rule. In that we are going to learn about two component system, that is zinc cadmium system. The sulfur system, it is a one component and four phase system, that is the four phases in which it exhibits are rhombic sulfur, that is Sr, monoclinic sulfur Sm, sulfur liquid Sl, sulfur vapor, that is Sv. So the maximum number of phase coexist in equilibrium is 3. Coming to the phase diagram of sulfur system, you can observe the phase diagram here. It shows the diagram of pressure versus temperature. Here the pressure on y-axis and temperature on x-axis. The phase diagram of sulfur system consists of 6 curves AB. You can observe the diagram here. AB is one curve, BC, similarly CD and BE another curve, and CE and EG. EG you can observe at the top. And the three triple points here, you can observe three triple points. One is B, second one is C, and another one is E. Totally three triple points. And coming to the areas, we have four areas. One is ABG. ABG is one area, and another one is BEC. BEC, and next one is GECD. GECD, and next one ABCD. ABCD. Now let us know one by one, that is curves. Curve AB. The curve AB is a sublimation curve of rhombic sulfur. SR means rhombic sulfur. This curve shows the effect of temperature on vapor pressure of rhombic sulfur. The vapor pressure of rhombic sulfur varies at different temperature. At 95.6 degrees Celsius, rhombic sulfur and vapor sulfur are coexist in equilibrium. Below 95 degrees Celsius, SR forms stable, that is rhombic sulfur forms stable, whereas above 95.6 degrees Celsius, monoclinic sulfur forms stable. So in this curve, there are two phases are coexist, that is rhombic sulfur and sulfur vapor. Coming to the next curve, that is BC. The curve BC is a sublimation curve of rhombic sulfur. It shows the effect of temperature on vapor pressure of monoclinic sulfur. It is a monoclinic sulfur. The vapor pressure of monoclinic sulfur increases with increase in temperature. Hence, BC, the curve BC curve bends towards the temperature axis. You can observe here, it bends towards the temperature axis. It bends towards temperature axis. It is a BC curve is a sublimation curve of monoclinic sulfur. You can observe here, this is not SR, it is SM. Slight correction in this curve, that is SM. Coming to the curve CD, vapor pressure curve of liquid sulfur, that is SL. It shows the effect of temperature on vapor pressure of SL, that is liquid sulfur. The vapor pressure of liquid sulfur increases with increase in temperature. At 444, that is 444.6 degrees Celsius, liquid sulfur starts boil when vapor pressure equals to atmospheric pressure. Therefore, the boiling point of SL, that is liquid sulfur, is 444.6 degree Celsius. Here also we have two phases which are coexist here, that is SL and SV. Curve BE. Curve BE is the transition temperature curve for SR and SM, that is rhombic sulfur and monoclinic sulfur. The temperature at which rhombic sulfur converted into monoclinic sulfur is known as transition temperature. The conversion of SR into SM is due to the absorption of heat from the surrounding. You can observe here conversion of SR into SM by the absorption of heat from the surroundings. This curve shows the effect of pressure on transition temperature of SR and SM. SR and SM. The transition temperature is increases here with increase in the pressure, hence this curve bends away from the pressure axis. You can observe the BE bends away from the pressure axis. BE, it bends away from the pressure axis. Coming to the next curve, that is curve CE. It is the melting point curve of SM, monoclinic sulfur. The melting point of SM shows effect of pressure on melting point of SM. The melting point of SM, here monoclinic sulfur, increases with increase in pressure. As the curve bends away from the pressure axis. You can observe the CE curve, it bends away from the pressure axis. CE, it bends away from the pressure axis. And the melting point of SM, that is monoclinic sulfur, is 120 degrees Celsius. That is, here also we have two phases which are coexist in equilibrium, that is SM and SL. Coming to the curve EG. Curve EG, which is at the top, it represents the melting point curve of SR, that is rhombic sulfur. This curve shows the effect of pressure on melting point of rhombic sulfur. The melting point of rhombic sulfur here increases with increase in pressure. When we increase the pressure, here also melting point of SR increases. Hence, EG curve bends away from the pressure axis. You can observe here EG curve is bends away from the pressure axis. Here the melting point of SR, that is rhombic sulfur, is 114 degrees Celsius. And here we have two phases which are in equilibrium, that is SR which is in equilibrium with SL. So in all these curves we have two phases and one component. So by applying the phase rule equation, we are going to get F is equal to 1, that is degree of freedom is 1. So it is a univariant. Coming to the areas. An area bounded between the curves shows the condition of two state variables here, that is temperature and pressure for one phase system. For one phase system. Area ABQ. Area ABQ. You can observe here area ABQ. Sorry, ABG, that is ABG, not Q, ABG, slight correction here. This area shows the condition of temperature and pressure for one phase system, that is SR, that is rhombic sulfur. Rhombic sulfur. And next one is area BCE. This area shows the condition of temperature and pressure for one phase system again, that is SM, that is monoclinic sulfur. And the next one is DCEG. Next curve is DCEG. DCEG. Here, this curve shows the condition of temperature and pressure for one phase system, that is a SL, that is liquid sulfur. Next area is the ABCD. You can observe here area is ABCD. Here, this area also shows the condition of temperature and pressure for one phase system, that is sulfur vapor, that is vapor sulfur. Okay, first one is rhombic sulfur, second one shows the monoclinic sulfur, and the third area shows the one phase system for liquid sulfur, and the last one shows the one phase system for vapor sulfur. So in all these areas we can observe one phase and one component, right? So by applying a phase rule equation, we are going to get F is equal to 2, that is degree of freedom is 2, so this is a bivariant. This is bivariant. Coming to the triple point, we have three triple points here in this phase diagram of sulfur. One is B, next one is C and E. Coming to the B, triple point B, it is a point at which three curves are meet, that is A, B, B, C and B. Three curves are meet, that is A, B, B, C and B, and three phases are coexist, that is SR, SM and SV. You can observe the diagram here, three phases are coexist. Coming to the point C, that is triple point C, here it's a point at which BC, CE and CD are meet. Okay, three phases are meet, curves are meet. Three curves are met, not phases. So, and three phases which are coexist here, that is SM, which is coexist with SL, and in which it is equilibrium with SV. And coming to the E, that is triple point E, which is at the top E, it's a point at which three curves are met, that is BE, EG and EC. BE, EG and EC, right? So three phases which are coexist in this point are SR, SM and SL. Okay, so we can observe a degree of freedom here, it is a 0 by applying a phase rule equation, because here we have three phases. So P is equal to 3 and C is equal to 1. So it gives F is equal to 0. So it is non-variant. It is a non-variant. Coming to the two component system and reduced phase rule. Okay, whatever we have discussed, it's about one component system. Now let us see the two component system. In case of two component system will be consisting of only two phases, such as solid and liquid, which are in equilibrium. Here gaseous phase is absent because the effect of pressure on equilibrium phases is very small, so that gaseous phase is absent. Therefore, in two component system, only two state variables are considered, such as temperature and concentration. There is no pressure. Okay, here there is no pressure component. So two component system which consisting of only two phases, that is solid and liquid, and gaseous phase is absent, is known as condensed system or reduced system. It is also called as condensed or reduced system. This reduced system reduces the degree by 1. Okay, degree by 1. Therefore, for two component system, condensed system or reduced system rule is given by F is equal to C minus P plus 1, because the degree is reduced by 1 here. That's why it is C minus P plus 1. In the previous one component system, it was F is equal to C minus P plus 2. Here it is C minus P plus 1. So F is equal to, we have two components, so it is 2 minus P plus 1. So F is equal to 3 minus P, where F represents the degree of freedom, C is number of components, and P is phases. So in that first system is zinc cadmium system. Okay, so it is a metal system with eutectic point. Okay, so it is a two component and three phase system. We have two components here and three phases. The three phases are, one is solid zinc, next one is solid cadmium, and another one is liquid solution of zinc and cadmium. Okay, coming to the phase diagram of zinc cadmium system. The phase diagram of zinc cadmium system consists of two curves, one is AO and another one is BO, and two areas, that is area above AO and above BO. You can observe here in the diagram, area above AO and above BO, and eutectic point, that is O. Here it is eutectic point. In the previous case it was triple point. Here it is called as eutectic point. And the last one is cooling. Let us see one by one here. First one is curves, that is curve AO. See the diagram here, you can observe the curve AO. Curve AO represents the freezing point curve of zinc. Freezing point curve of zinc. The point A here represents the freezing point of zinc, that is 419 degrees Celsius. The curve AO shows that melting point of zinc is lowered by addition of cadmium. By the addition of cadmium, it lowers. The melting point of zinc is lower. So here the two phases are coexist, that is solid zinc and liquid solution of zinc and cadmium. Coming to the curve BO, see the diagram here, curve BO. Curve BO represents the freezing point curve of cadmium here. It is cadmium, this is for cadmium. The point B represents the melting point of cadmium, it is 321 degrees Celsius. The curve BO shows the fall of melting point of cadmium and the addition of zinc. You can observe here fall of melting point of cadmium and the addition of zinc. So here we have two phases which are in equilibrium. One is solid cadmium and liquid solutions. So here we have two components and two phases in these two curves. Okay, So by applying a reduced phase rule, it is F is equal to C minus P plus 1. So F is equal to 1. So the system is univariant. Coming to the areas, we have two areas. One is above AO and another one is above BO. The first one, area above AO. In this area, both the components, that is zinc and cadmium, are present as liquid solution of varying composition. The solution of two metals being homogeneous and constitutes one phase only. Here it is homogeneous, so it is one phase only. Coming to the area above BO. In this area, zinc and cadmium exist as liquid solution and represents one phase only. Here also. So by applying a reduced phase rule, we have F is equal to C minus P plus 1. So F is equal to 2 here. Okay, F is equal to 2. So this is a bivariant system. In these two areas, we have bivariant system. Coming to the eutectic point. What is this eutectic point? The curves AO and BO, okay, at O, they are meet each other. Okay, they are meet each other. Here solid zinc and solid cadmium and solution of cadmium and zinc are in equilibrium. These three are in equilibrium. So there are three phases at this point. You can observe here solid zinc, which is equilibrium with solid cadmium, in which it is equilibrium with solution of zinc and cadmium. So by applying reduced phase rule, here we have three phases and two components. Okay, so it gives 0, F is equal to 0. So the system is non-variant. F is equal to 0 means non-variant. So coming to the cooling effect here. See, if the solution in the area above AO, observe the diagram here. If the solution in the area above AO is cooled, zinc separates as the curve itself is reached. Okay, zinc is separating here. This continue till the point O, when the solid eutectic mixture, that is 83% and 17% plus 17% separates. Similarly, the solution above BO on cooling allows the separation of cadmium here. Here the separation of cadmium takes place. This continues till the point O is reached at 270 degrees Celsius. And eutectic mixtures separates. These two mixtures are separate. Coming to the revision of this session, today we have discussed about phase equilibria in one component system, that is sulfur system, and we have also discussed a reduced phase rule, that is two component system. In that we have discussed phase diagram of zinc cadmium system. These are the references. Thank you.